Just say.
In fact, we've been doing it for almost 10 years. So the point about it's unproven, it's untried, it's untested is it's just not true. At the end of this, I've done this now, I think this is the fourth time I've given this talk, but there's a lively discussion to be had about the costs, about the scale up, about risks, about who pays, and I'm happy to talk about that at the end. But the one thing I want you to take away from this is we can do this at a large scale. We've been doing it at a large scale. So it does work, and it's not unproven. So I'll just mention, I'm going to mention, so the title is really, geology and hydrogeology part of this project. It's a huge project. And I mentioned one of my grad students who did the hydrogeology groundwater monitoring program. And I'll just also mention that I have listed a whole bunch of co-authors here. And the way this project works is, the Petroleum Technology Research Center is a sort of a strange animal that exists through funding through various agencies. And its function really is to collect money from all kinds of companies and then facilitate research. So I happen to sit on a board or a panel or a committee that is called the Science and Engineering Research Committee. So basically, we have a geophysicist, another rock mechanics guy doing simulation stuff, another geologist, another rock mechanics guy. We have geophysics, fiber optic people. So we have a whole bunch of people that sit here and basically direct what happens on this project. So this has been going on now for 15 years, and we've done a lot of work. And so at our annual meetings, this talk can take a week to talk about every aspect. And so I'm going to just show you a few flavors of geology and hydrogeology, this project, and then a couple of highlights from what we found. So, come on.
Again.
I don't know what.
Oh, sorry, I was on Zoom trying to sort out the audio.
Okay, I didn't touch it.
No, go.
There we go. Okay, so the setup for this, and this is the public part of this lecture. Essentially, you hear lots of talk about global emissions, okay? So, and I think this is data-based that, CO2 is an important greenhouse gas. There's no doubt that anthropogenic emissions are going up, and there's no doubt that those CO2 levels in the atmosphere are going up. Those are data points. And so this is just some graph from a couple places showing back the 1700s, but this is a more recent data set from NOAA. Probably, I think this is the Hawaiian Observatory. You can see that sometime early in the 2014 or so, we crossed this 400 ppm CO2 in the atmosphere. And so what I want to make really clear in the rest of this talk is there's a worldwide concern and effort to reduce emissions, and we're not going to talk about the argument or the religion about human-induced or not induced. We don't care about that. We're gonna put our hats on and say, we need to be reducing these emissions because at the least, we don't want to be putting bad things in our atmosphere. So that's really the setup is globally, people have started to work on doing these reductions in CO2. Now, when you start talking about global reductions in CO2, it's shocking to a lot of people to realize the scale of the problem. And there's the most elegant paper that was published in 2004 that does a great job in public terms to display the scale of the problem that we're after, okay? So if you haven't read this paper, I would urge you to download this and read it, because for many years, 20 years ago now, this was sort of the rage. And I'll just explain what this paper is all about. So on the vertical axis, pointer here, is a graph of basically global carbon emissions per year, and the scale goes from 0 to 8 to 16 billion tons of carbon, so gigatons of carbon. And here's a time scale, 1950 to 2100, and at the time this paper was published, it was 2004, and there was more or less this sort of steady increase in carbon emissions globally, okay, so you can see this. So these guys proposed a concept to say, what do we have to do to stabilize these emission levels? And so they invented this thing they called the stabilization triangle, and the sub part of that is called stabilization wedges. And so their kind of working model was, what do we have to do in the earth to end up in 50 years back where we are in 2004 with global carbon emissions? So you can imagine, we're going to do a bunch of pathways in here so that 50 years from now, we're going to get back to starting at square one, okay? We're not going to do any reductions. What do we have to do to get back to where we are right now? And so what that becomes then is a triangle of CO2 reduction that you have to do globally, okay? So to break that into bite-sized pieces, they did this elegant kind of analysis that basically says, okay, we're going to create these things called wedges. And it just works out that if you're at 2050 with 16 and you're here at 8, you need 8 1 gigaton reduction bites in 50 years. Okay, so they coined this term called the stabilization wedge. And really what a stabilization wedge is, says, what do we have to do for 50 years to cut 1 gigaton globally? And that ends up being 25 gigaton cut. And how do we do this? Okay, because what is the gigaton of carbon? Well, and then you start looking at the scale of this problem. So they said, first of all, we're going to look at solutions to the CO2 reduction problems that can get us at least one of these wedges. So if you invent some kind of laser-based space technology that, messes around and does something, it has to be able to do 1 gigaton of carbon in the next 50 years. Okay, so you start to say, all right, so let's imagine that if we had a carbon tax of $100 a ton, what is one of these wedges worth? And it turns out if you multiply 25 gigatons by $100 a ton, that's a $2.5 trillion wedge, okay? That's a lot. Now, it gets a little scarier because really they revisited this in 2011. So they, wrote a paper and said, okay, how have we done after 7 years of talking about this? And the bottom line is by 2011, nothing had happened. And now we needed 9 wedges in the next 50 years. So in other words, to get to 2061. And I updated the data in December, and the latest data from 2023 are that we now need 10 wedges in the next 50 years. Okay, so we're not getting anywhere with our wedge reduction strategies. So that's not good news. But what, back to this 2004 paper, so they proposed that they could think of 15 strategies to get a wedge, okay? So remember, you need 10. You got to get 10 wedges to get back to where we are today, not make any global cuts, but get back to where we are today. So this whole paper and then their research group's effort for the last probably 10 years or more has been to look into each of these things and what do they all mean. Now, this is a talk about CO2 storage, so we fit in here under CO2 capture and storage with the possibility of doing 3 wedges. So I'm going to talk about that, but I'm just going to give you a flavor for some of these other ones. And if you want to learn more about all 15 of them, you have to go to the Princeton Carbon Management Institute's webpage. So here's the way to get fuel efficiency to get 1 wedge. And so this is in 2004. So I'll just point out a couple of highlights here. So one way to do it is to take all of the electricity produced in the world and double the efficiency. And that means you get one wedge. Take 600 million cars in the world and either have the miles that they travel or double the fuel efficiency of every one of those 600 million vehicles. Okay, so that gets you one wedge, and you need 10. Or basically improve the energy efficiency of all residential and commercial buildings in the world, and that gets you a wedge. And here's just a sidebar. So replacing all the world's incandescent bulbs with compact fluorescence gives you 1/4 of one wedge. That's every light bulb in the world replaced with high efficiency light bulbs gives you 1/4 of a wedge. Other people like to talk about natural sinks of carbon. So let's talk about that. So let's stop all tropical deforestation in the world. That gets you one wedge. You got to come up with 9 more. Let's plant new forests over an area the size of continental United States. So let's reforest every single square foot of the United States, you get one wedge. Don't allow any of it to burn, can't log any of it. That's what you need to get one wedge by natural sinks. Or use basically conservation tillage on all cropland in the world. So you can see that, we could maybe get 1, 2, 3 wedges if we stop deforestation, plant trees over all the United States, and did conservation tillage, but we still need 7 more wedges. Okay, that's a tremendous eye opener for a lot of people. Now, my part of it is no better than that. So carbon capture and storage, in order to get a wedge, we would have to do CCS at 800 coal-fired power plants, 1,600 natural gas electric plants, 100 coal-fired power plants, or 10 times the capacity of all hydrogen plants in the world. And so in the 2004, basically there were, a handful meaning like 3, that were doing more than 1 million tons of CO2. And by 2055, so in 50 years, we need 3,500 projects around the world doing more than 1 million tons a year. So can we get a wedge by CCS? Remains to be seen. We have 50 years to do this. Whether it'll get to 3,500 or not, that's 1 ton per year. So again, if you do a 5 ton per year, you need less than that in number, but it's a big number and a big dollar event. So, like I said at the very beginning, I'm here to talk to you about, can we do this from a technical point of view, whether society will do this, we could talk about that. But we have done this at a project called the AQUISTORE project. And so I mentioned that AQUISTORE is managed by Petroleum Technology Research Center in Regina, Saskatchewan, and I'll point out where that is. And it's done in conjunction with SAS Power. So SAS Power is a provincial utility that basically provides all the electrical power under government license for the whole province or the whole state. So there's no private power generation in the province. It's all done through one big government utility. And the idea behind the AQUISTORE project was to put carbon capture on one of their commercial scale power plants. And then they're going to sell some of that CO2 to the oil industry for EOR purposes. And part of that's going to end up back in our research well. And we're going to then develop strategies for injecting this, monitoring it, and verifying it in the subsurface. Okay. So really the project was all about, can we take a commercial scale capture project, put it in the ground, and then monitor it and demonstrate safety, demonstrate costing, even to the point of looking back after we've done this project. Now, after 10 years of doing it, we're looking at least amounts of data. So what's the minimum you need to do to get to the same outcomes where we're at right now? So lots of research things, but we're working with a functioning power plant, and that puts us into all kinds of interesting things. So to set the stage where we are, we're down here in Kentucky. The Williston Basin covers sort of Saskatchewan, most of North Dakota, the eastern part of Montana, and northern part of South Dakota. So it's a big, large area of sedimentary rocks. Deepest part in the basin is in Williston at about 6 kilometers depth. Where we are here in AQUISTORE, it's about 3,400 meters deep, so 10,000 feet or so. And what happens is the coal fired power plant is at this red star, and then they send CO2 along this pipeline, which heads north, and it gets to a junction box. And at the junction box, they decide how much goes up the pipeline to the oil field for storage, and how much goes back to the injection well. And depending on the day, how much CO2 is being produced, because the power plant goes up and down with its power needs. And then depending if the oil company is doing maintenance and they don't want CO2 that day, they put the whole thing back in our well, or part of it, or none of it goes into our well. So our injection rate in the wellbore goes up and down way more than we ever wanted. But it does, that's what it does. This is a real project. So here's the picture that I think Alan sent out to most of you. So this is an actual functioning power plant. The original power plant was built in 1968. And this actually has, this is the Boundary Dam Power Station. So this produces 25% of the power to the entire province of Saskatchewan. So it's a big, big power plant. There's a coal mine right next door. They take the coal, they pile it up here, they send it into this thing, and depending on the power needs, they'll run 1 to 4 of these power plants. And then this center here part is a flue gas capture that runs to an amine extraction column, and then there's an amine recycler here, and then this is the compressor station, and it runs into an underground pipeline off the picture like I showed back there. So I'll mention that this thing was originally 139 megawatts for this unit one right here. This is one we're using, unit 3. And they redesigned it to be 150 megawatts. And then when they put it on with the full carbon capture working with full compression, it generates about 120 megawatts of power. So it's full commercial scale running power. Now, they had to retrofit this thing, and part of the cost, if you dig into the internet, they ran into all kinds of problems when they were retrofitting this thing with things like asbestos and lead paint that they had to then update environmentally. So they had a challenge to do the retrofit, even without putting the carbon capture unit on. And it went from basically 0 scale to full scale in 1 step. So you imagine they paid quite a penalty for being the world's first full capture carbon capture coal-fired power plant. So this is really the world's first. And it started testing, they commissioned everything in 2013, didn't really start ramping up until later in the year, and we started injection later. So what I want to show you is a flavor of some of the geology and hydrogeology that we've done in hydrochemistry, and I've broken it into 3 parts. So characterization at AQUISTORE, so stuff we did before we drilled the well, then stuff we did when we drilled the well and some of the testing, and then a lot more of the details will be in the monitoring we do since then to prove that this is sort of staying in the ground and it's sort of going where we said it would. So again, finally got capturing in 2014, commissioning, retrofitting, and we started injection in 2015. And then we've had this sporadic injection since 2015. And I'll say it again at the end, we just passed 600,000 tons injected into one wellbore. So we're getting up there in terms of injection. So pre-drill, we're fortunate in Canada, in this part of the world, that we have access to all the public oil and gas well information. Every well that's drilled gets turned over to the government after a certain period of time. So we're able to do old-fashioned geology. So geological mapping for structure, cross sections, facies, aquitard maps, porosity, permeability data, regional hydrogeology. So I'm showing a chemistry map and regional flow mapping. So looking at where the fluids are going in the entire section of some 35, 40 aquifers, and I'll show some pictures of that in a second. So we have access to all this data, including 11 wells drilled through the entire section in the area, although the closest one was some about 15 kilometers away. And the reason we did that was we didn't want to have any well bores penetrating the cap rock of our system. Now, the good news is we have no penetrations. The bad news is you're doing exploration basically because you don't know what the reservoir is like. The other thing we have there is seismic data that's available for purchase. So we can buy, trade seismic to enhance our information in the area. So lots of data to work with to cycle these things. And then the first thing that you do is you take your best estimate where you're going to put a well, you take the rock properties, the thicknesses, the permeabilities, all those things, and you put it into some very crude numerical models and you play what if games. So inject 2,000 tons a day for 10 years and look at how big a plume would you expect to see. So here's a 10-year simulation. And then the idea behind this was not to necessarily use this to say, we think it's going to do this. The idea behind this was to use this to understand how big an area we needed to monitor over the life of the project. Okay, so how big do you want to design your monitoring network? So we use this to design the seismic surveys, the groundwater modeling programs, soil gas, all these programs that we did. We used these early crude simulations. And one of the fun things is to go stack these all together and look at, what did we do the very first day with no information about the site? And then what do we know now? And it makes a humbling experience. So for example, this is one example with seismic survey. We were able to take trade, oil and gas industry 2D seismic lines and purchase them over our area of interest and then create a pseudo 3D merge of all those 2D lines. And of course, the geophysicists, we did this because first of all, we know that the Precambrian basement rock is quite variable. There's quite an unconformity there, 1 billion years or so of erosion and uplift and all kinds of things. So we wanted to make sure there was going to be a reservoir there. So is there going to be a thickness of, the sandstone, the basal sandstone on the surface of the Precambrian is going to be there? Were there going to be fractures or faults at the reservoir level? And then above it, are we looking for major discontinuities in the sealing layer? So are there any faults? Are there any, collapse features, anything like that? And it turned out after that exercise, we convinced ourselves that this looked like a pretty good spot. So that gave us the go-ahead point, and we actually went and shot our own 3D seismic. In fact, we shot 2 of them. And the reason we did this was to check. One part of this project was we actually buried 620 seismometers in the ground, so geophones in the ground around the site. And the idea behind that was the geophysicists argued that the co-location errors on these 4D surveys were very large. So we actually have a way to keep those co-location errors. In other words, every year you shoot a repeat seismic survey, you have to worry about where your shot points are compared to the year before. So we can actually turn on 620 of these that are fixed in space and measure that. So we acquired a really detailed seismic survey. I'll let you worry about that if you're interested. Talk to our geophysicists over our project area. And from that, we did a whole bunch of processing. And this is just one example of a time slice converted to a thickness slice for one of the secondary seals. So here's our proposed area. And you can see the color in here. This is an evaporite layer. I'll show you where this is later. That's like 150 meters thick. And you can see, we know that there's some fins in this layer, but the isopack looks pretty good above our storage site. So we're pretty happy with this as a secondary seal. And of course, I don't know how many layers, 64 layers they processed in this whole thing. So a lot of seismic. And I'll just summarize that by a cartoon like this. So here is the entire section from surface to 3,400 meters deep. And we're sitting in the Deadwood Formation. So that's a basically basin-wide sandstone layer deposited right above the Precambrian basement. And then above that is our primary cap rock. And then above that are a whole variety of layers that the oil and gas industry chase after. So here's the Manville, these Midale beds, the Bakken, Red River. These are all oil and gas targets above where we're injecting CO2. And then the good news for us is we have a whole series of stacked, horizontally continuous seals. And so we have a primary seal, and we'll look at that in more detail, but here's this salt layer. So 150 to 200 meters thick halite that sits in the basin. And then there are, like this is, for instance, a regional seal that traps all the hydrocarbons in the basin. So that's holds back 5 or 10 billion barrels of oil in the basin. So that's a really good regional seal. And then above that is about 800 meters of Colorado group shales that isolate basically the farm wells and the shallow aquifers from this entire package of rock. So when you talk about people injecting CO2 down here, will it impact the near surface groundwater up here? It's very difficult, even if you try to migrate a molecule of CO2 through that section to the surface. Okay, so it's a good place to do CO2 storage, 30-foot fall fields, end to end, all the way to depth. Okay, so we're convinced of that enough to drill 2 wells. We drilled, the first well was our injection well, 3,396 meters deep. Started in early July in 2012. It took us to almost the end of September to get to the bottom. And then we started about 2 weeks later in October and drilled a companion well 150 meters away in a little over 5 weeks. So we learned in one iteration already how to drill these things faster and do it way cheaper for the second well. And I'll mention here as an aside, in 2012, we used to say these are the 2 deepest oil and gas wells in Saskatchewan. And a partner geothermal project took our data set, moved about 10 kilometers south of us and drilled wells approximately 30 meters deeper than us. So they could claim they were the deepest wells drilled in Saskatchewan. So we're happy with that. Good for them. But it was a lot of fun hanging out at the rig for a whole summer. If you do any kind of subsurface geology, geoscience, this will make sense. So, you know, we cut 3 cores in the well, 48 meter full diameter, 3 different ones that summed up to 48 meters, and 30 sidewall cores. This is going in and taking core plugs out of the various horizons. Then geophysical well logs were used extensively in this. So if you do any kind of deep subsurface geology, standard geophysical well logs. So SP logs, gamma ray, resistivity, sonic density, those are normal. You do in every borehole. And then we did a whole bunch of really, we call fancy well logs. So full waveform sonic, NMR, formation micro imaging, sidewall scanning. So basically do an image of the borehole wall. And then those are expensive, very complicated well logs. Fortunately enough, we were able, as a hydrogeologist, to collect 4 downhole fluid samples along with pressures, and as well as a mini frac. And I'll show details from those fluid samples because they're part of the story that is important. All those well logs showed us that we had 188 meters of reservoir thickness that we could work with. So within that, we perforated 88 meters of those interval in our 188 meters of thickness. And, you know, we perforated 4 injection wells. I had about 2 hours to pick the perfs for this project. Well, the drill rig was waiting for us to say, okay, where do you want to perf? And the standby time was $75,000 a day. So they're like, take as long as you want. We'll wash our pickup trucks and you can decide where you want us to do, what you want us to do next. So we didn't have a lot of time to do this. And we probably wouldn't do 4 injection wells again. And we definitely wouldn't have perfed as close to the basement as we did then because we didn't know any better. So just to show this, I won't belabor this too much because I know it's hard to imagine. So here's the Precambrian basement. This is basically granitic, gneissic, you know, sort of rocks at the basement. Here's our main cap rock at the top up here. So this is the Ordovician age shales at the top. And then we have an upper sandstone layer that has porosity in it. And then this deadwood package. And for those of you who aren't aware, this is, for instance, the gamma ray log. So this shows sandstone on the left and shale on the right. So you can see this blue area is where it's permeable, a little bit of permeability, and then a lower part that's permeable. We cut a core over this interval. We basically cut sidewall cores through here, and then we cored the interface between the cap rock and the top of the reservoir to understand reactions at that seal boundary. So the other part is that 150 meters apart, we have 2 sets of well logs, and it's hard to find a difference between the geology of those things. So very continuous layer cake stratigraphy. And you can do all kinds of interpretations of mineralogy, permeability, etc. It's a great exercise. But that's what we found when we drilled the wells. Now, just to give you some idea of the details of some of this, so in our coring program, we did sort of standard, 14 meter diameter, 14 meter core box that was then subjected to a whole variety of tests, every test you can imagine. This is one example of our image sensing that gives us the distribution of carbonates versus quartz using modified, I think this is infrared or some kind of remote sensing description of the core. So, you know, you can pick the difference between the carbonates and the quartz layers out of the sandstone layers versus carbonates out of here. The second core was subject to much deeper, much more traditional kind of facies analysis that geoscientists would do. So logging the core, coming up with core plugs for permeability and porosity measurements, doing facies analysis, trying to come up with a facies model, and then subjecting this to, you know, gas permeability, liquid permeability, gas porosity by different methods. So we have lots and lots and lots of data on perms, and you can see, you know, we have some pretty permeable intervals in this core. That's 300 millidarcy permeability. Some of them are pretty high, and you can pick how you want to average these things. It's a pretty good, this is a pretty good part of the reservoir. Going up one level in terms of scale, so you got core plugs. Now you can do dynamic tests. So these dynamic tests are like small scale pumping tests. So this is a device that is pressed against the borehole wall. And this center valve is opened up and flow is allowed to collect fluid samples, as well as do permeability measurements, as well as do mini-frac to determine in situ stress distributions. So we're able to do that and scale that all with the sidewall data. So lots of integration of this. And I'll just mention the results of these downhole sampling because we were able to show that these horizontal layers are isolated over geological time. And so just to show you this, so here's 4 samples. We repeated the first sample to show that you could do this and it wouldn't change once we'd gotten a good sample. And then we did 2 more intervals deeper in the well. So you can see we did 3197 twice, 3233 and 3310. So these are hugely saline brines. So 320, 330 gram per liter brines, sodium chloride, calcium brines. So 200,000 chloride, 90,000 sodium, and you start to see the first difference. So in the Winnipeg formation, 24,000 calcium versus 32,000 in the Deadwood. So that's significantly different. But when you look at some of the trace elements and all the list of isotopes and things like that, you'll see these are different waters, okay? So you can see, say, call that 800, basically strontium in the one layer and 1,000 in the one below it. Manganese at 36 to 38 versus 100. And look at the lithium values. So 50, around, I call that 60 versus say 35 in the deeper zones. So these are, from a storage point of view, geologically, these layers have been isolated for hundreds of millions of years. That's good news for storage. Now, the final part, you know, my colleague, Rick Chalternick, just did an SPE distinguished lecture tour, and I'm sure this one slide was his whole talk, okay? So basically, if you can imagine numerical modeling and integration with every possible type of model you can think of, looking at geostatistical realizations, looking at, you know, machine learning simulations. So just as an example, this one top diagram here is one of Rick's group built a fully coupled 3,400 meter high mechanical earth model with full temperature coupling in stress and strain to look at, you know, thermal effects on deformation of rocks. So thermal stresses. And so that's one model. The other models are, you know, pick your flavor of Petrel, pick CMG, pick any of these. We did mod flow models of this to prove that you could use mod flow to help show the same kind of thing that they're doing with these fancy 3D reservoir simulations. So a lot of numerical simulations used to predict the plume movement and prove conformance of the CO2. Now, final then, so post-drilling. So a lot of the post-drilling work that we did, hydrogeology, hydrochemistry, was used as the baseline surveys for the monitoring programs. So we measured everything for 2 years before we injected any CO2. And so things like background microseismicity. So we measured microseismicity at the site for 2 years before we injected any CO2. Lots of vertical fancy seismic, so cross borehole tomography, 3D VSPs, all that kind of good stuff. And then from the sort of hydrogeology, hydrochemistry side, you may be more familiar with this, we measured soil gas and soil gas sampling devices. Again, 2 years worth of soil gas measurements. continuous vertical, continuous horizontal, all kinds of good stuff. Shallow groundwater programming I'm going to talk about, and then a ground deformation study. So we use GPS instruments, and I'll show pictures of that. We use INSAR, so that's radar, satellites, and we were able to measure sub-millimeter deformation of the landscape 2 years before we put in the injection. So we actually are measuring glacial rebound of our site for 2 years before, and actually the horizontal displacement kind of freaked us out. So we're actually able to measure plate tectonic movement of Saskatchewan from space in the time we were doing this. Crazy, crazy stuff. Okay, so this is, you know, the meat and potatoes of what we're doing. So we installed traditional piezometers, and then here's one of these INSAR reflectors. We learned very quickly that cows seem to like scratching against our INSAR reflectors, so we had to fence all these things in. Otherwise, it makes a mess of your, you know, fancy satellite measurements. So these things are detectors that are read from space, and they can measure sub-millimeter deformations of the land surface. It's crazy. And then there's GPS monument here, and that thing, again, these are both buried down about 30 meters in the ground. So they're attached all the way down below the frost depth to make sure that we're not seeing movements of frost. So tilt meters. And all this stuff is collected, so soil gas monitoring devices, all these things, there's actually newer ones in here that are near surface CO2 sniffers that collect into this network as well. So these things are all telemetered back to Ottawa and recorded in real time and analyzed for signals. Soil gas, we have a big argument about soil gas. Alan was giving me a hard time earlier. One of the other projects we were involved in was a controversy over soil gas measurements. So we do a lot of soil gas, you know, including, for instance, measuring carbon-14 on soil CO2. And it doesn't work very well here because this part of this site is reclaimed coal mine spoil. So of course, the coal is affecting the soil gas values, but we measure it. And boy, you know, if anybody ever accuses us of having leaks, we have enough data here to go to town on. The other one, of course, when we first started, everybody was worried about wellbore integrity. So we put all our soil gas around the wellbores to make sure we have no leaks up the boreholes. But in the 10 or 15 years we've been working on this, the focus has shifted to microseismicity. So everyone's worried about microseismicity. So we have 620 seismometers, and this just shows you we monitor this cross selection of about 30 of them in real time. And you can imagine one of our geophysicists who does this, Anna Stork, you know, this thing collects however you want it, every 15 minutes, every minute, forever. And we have to pay a guy to go out and change the batteries and download all the data every day, or every month. It goes out once a month. So they also put in multi-band seismometers. So we have a whole bunch of these multi-band seismometers in there, measuring for every, you know, any possible cracks, snaps, and pops in the subsurface. And when we gave a paper on this at a conference in 2018, everybody accused us of our system not working because we reported basically there's no detectable events. And they're like, wow, maybe your system's broken. So we had to then go back and put in the daily mine blast that happens every day about 2 o'clock in the afternoon. We had to put in some of the big worldwide earthquakes that our system detects beautifully. And so we filtered all those out. We wouldn't do that again. So no detectable events. Now, lots of discussion about why that is. We're probably injecting at a fairly slow rate, or you know, we have a good reservoir to put it into, and it's basically a seismically inactive area. But this is the big concern now of the whole world, is microseismicity is everything. Now, I'll talk for a couple minutes about the geology monitoring, because this is where one of my grad students spent, you know, 2.5 years out there doing this. We took the 3 or so kilometers from the injection site to use as our area of interest for monitoring groundwater. And then we basically drilled a bunch of wells for hydrogeological baselining and hydrochemical baselining. And then since that time, so she installed it, did the first baseline studies for her thesis. Since that time, she went out and helped us monitoring. We did every 6 months at the start, and now we just go back every year and do this kind of monitoring. And what's unusual about this is that we learned a lesson from earlier CO2 injection projects that you have to get public buy-in. If you don't get public buy-in, you're gonna be in big trouble. So we actually, in one of our open houses, so this is just to show you a radius around the injection site, you'll see a bunch of these DW wells in red. So these are actually drinking wells from the local farmers that live in the area. And so we actually engage them in the monitoring program from the very beginning. We go to their house, sample their water well, we give them a copy of the results, talk to them about what the results mean, to show them that their water has not changed chemistry at all in the 10 years since we've been doing this. And they're very happy with that, to the point where one of these landowners said, yeah, I believe you guys, just don't blow up my water or something. So they stopped participating in this thing. Then we used some pre-existing deeper wells, some on-site ash lagoon wells for the monitor. And then my student drilled 19 of these piezometers in a cross. Here's the site at the center. So we drilled these things, and then these are the ones that we monitor. All of these we monitor every year, usually in September. So just to show that we do have some hydrogeology on this, I won't belabor all the details. This is down about 40 meters deep. So from surface to the deepest wells. The flow is controlled by local topography towards local streams. It's not a surprise. I mentioned that they did some coal mine remediation at the surface. So they've taken out some of the shallow surfaces is backfill from tailings from the mining operations. So essentially, the majority of the groundwater flow in the area is in the top 30 meters of the landscape. Now, this is the interesting part of the story for groundwater monitoring, is that the groundwater quality from a farm well or drinking water standard in the area is terrible. So the farmers that live out there have to have incredible water treatment systems attached to their wells. So you can see that, some of these farm wells have total dissolved solids of 5,000 milligrams per liter with very high sulfate and high sodium. So sodium sulfate waters. We think that it's associated with gypsum dissolution and clay reactions. So calcium and sodium exchange on clays and things like that. And then of course, the strip mine areas have also very high TDF water because of the disturbance of the soil. So that's the bad news. The good news is that when you monitor the water chemistry is so stable, you can use the water chemistry result to detect lab errors in the analysis. Okay, so here's, from 2013 to 2023, and you can see, it's like a ppm or so variation in most of these parameters that you measure for 39 different wells with stable isotopes, 13 CDIC isotopes. It's as stable and boring as you can get. So that's good from a point of view of storage and monitoring. It's kind of bad from a science point of view, because what do you write a paper about? Oh, well, it didn't change from last year and the year before, the year before, the year before, the year before. So that's sort of boring. And my colleagues in our research project, when I have to stand up and present this, the regulators in the room, they want to see that nothing's changed, but scientifically it really is boring because nothing's changed. So that's good. So we'll take that. It's a win. So finally, the current update. So where are we? Well, we started in 2014. We injected 600,000 tons so far. We monitor all the time, so that's great. And we've got a couple of interests that you only get from one of these full-scale projects. And so the first part I'll show you is some of our seismic results. So we're well known for this worldwide because of, again, this installed dedicated monitoring system, as well as doing these surveys. So what do we do here? Well, we're using amplitude, so seismic amplitude difference. So between the baseline survey and the injection zone is 3,400 meters deep. So we do a seismic survey, and then they subtract these images and do the difference between the images to obtain the anomaly. So you can see here that we did 2 baseline surveys to establish the noise in the monitoring system. And so you can see that, there's some noise here and there, you get noise. And this is related to surface effects, drainage ditches, roads, houses where you aren't able to measure things like that. So you expect some noise in these samples. So the first image, again, between 0 and 36,000 tons, you can start to see there's the injection well, there's the observation well, and it seems to be going where we would expect it to go, and going in about the radius we'd expect for 36,000 tons. 102,000 tons, you can see some noise. Whether this is a discontinuous blob, we think it's probably noise, but this part seems to be behaving properly. Then you go to the next one, and you can see the 141,000 ton survey was really noisy. So we don't trust any of these ones out here, but you can see that this blob is now getting where what we would expect, heading up dip. And this one, we've spent 5 years arguing whether that's real or not. Most people think that it isn't real, but this one is a much better behaved survey. You can see there's a lot less noise. And this sort of linear feature right now here is the subject of much debate in our communities. And we just finished shooting the 600,000 ton survey. And I missed the conference call last week where our geophysicist presented the results. I don't have that slide. I'm trying to get it, but you can see that, you know, this is what we then use in the machine learning algorithms and the numerical models to try and update the estimates of permeability to match this kind of plume that exists in the subsurface. So it's doing pretty well, like what we'd expected. We expected it to be within this sort of red circle, and it seems to be doing that. So that's good news. Good news. Now, that's the good news. We also get some things that we don't understand. And this is kind of an interesting graph that we've spent a lot of time and a lot of discussion with other people doing this in the world. And so I'll explain what this is. So the idea is that if you plot, so the setup of this is you're injecting at a constant rate and you monitor bottom hole pressure. And so all things being equal, if you inject at a constant rate and you measure the pressure, it should stay the same. But what we find as we inject, the bottom hole pressure will actually fall. And that implies that we're changing the permeability as we inject. And so if you plot, basically, so this is injectivity value. So this is basically porosity, permeability, density, viscosity, skim factor as an index. So that should be constant. And if you plot that versus temperature in the subsurface, what you see is you start off here at, it's about 110 degrees bottom hole temperature. And as you inject cold CO2, you start to cool the subsurface. And as you inject and you cool the subsurface, and now we're down to 70 degrees bottom hole temperature because we're injecting supercritical cold CO2, actually the injectivity of the well goes up. Now, if you shut the well in and let the wellbore recover and heat up again, injectivity falls down, and each of these traces then is one of these cycles where it actually goes back up to this kind of value. So if you think about what could cause that, right? What are we doing to the subsurface? So we've had arguments about the equation of state for supercritical CO2 doesn't predict the density properly, porosity doesn't work. I mean, what are we doing? The thinking right now amongst our team is that this reflects thermal fracturing near the wellbore, okay? So as we cool the near wellbore, it creates thermal stress near the wellbore that causes microfracturing that increases the permeability that allows CO2 to get into the formation easier. Now, I can tell you that Shell doesn't agree with that, and BP doesn't agree with that, although they see exactly the same behavior in their wellbores. So there's a bit of a discussion going on about what causes this sort of behavior, and to be quite honest, we don't know. So we have PhD students and postdocs working on thermal stress models to figure out what is this? What are the implications of that? Interesting. Real project. You don't get to see this if you're doing theoretical simulations. You don't get to see this if you're doing 1 ton of injection. You need to have lots of injection over long periods of time. The second thing that comes out of this is some really interesting geochemical behavior. So what we did periodically is we run downhole cameras down our 3,400 meter deep borehole. And when we first contracted this, the client said, oh, you know, 3,400 meters deep in an oil and gas well, it's going to be dirty and we won't see anything, except we have a column of supercritical CO2 in the wellbore. It's crystalline as all get out. So when they run this camera down, it has its own lights here, and you get a crystal clear image. This is the inside of the steel borehole, 3,400 meters down. And when we got down to the bottom, you can see, for instance, this is what it looks like inside a borehole. These are perf holes where we perf to inject the CO2 out of the wellbore. But some of our perf holes have these really crazy sodium chloride stalactites hanging off the inside of the wellbore. And when you go further down in some of the perf zones, they get so big, they actually block, these balls block. And so the tool knocks them all off at the bottom. Some places it's completely occluded the perfs. Now, the interesting thing is, the geochemists tell me that that pinkish mineral right there is solid form calcium chloride, which is Antarctica. And that only is supposed to exist in Antarctica at very, very low temperatures. Except this is 110 degrees Celsius in a column of supercritical CO2. So this is like, this shouldn't be there. And we're trying to get pieces of this with a basket to actually confirm that. But the question is, what causes this behavior? And what we think is going on is that when we're injecting, we're pushing CO2 away from the wellbore. And as soon as we shut the well in, basically the formation pushes CO2 back towards us. And if any water comes into that column of CO2, it precipitates salt immediately. So these are actually salticles hanging on the inside of our wellbore. So the takeaway message, right? Never stop injecting because you plugged your borehole up, right? So we've even thought about when they do maintenance on the well, you need to get a tank of CO2 and keep the pressure, keep that stuff away from the wellbore. But this behavior is, again, one of the things that you don't see in theoretical modeling. You don't see in a pilot project. You only see behavior like this in a real operational project. So lessons learned that are being used in these projects around the world are things like this. So with that, I'll wrap up and say the final conclusion then is, we've been able to demonstrate that you can capture CO2 from a commercial scale power plant. You can put it in the ground and you can monitor it. We've been doing it, it works, and it's not pretend. We've put in 600,000 plus tons. It's a great spot to do geology and hydrogeology. We continue to monitor this injection. The plan is to move this forward another 20 years or so. We're seeing all kinds of things that you learn by doing a real project. But, overall, this has been a great project to work on. And one of the things we're working on right now is we're going to drill another well. We can get the money. And the idea will be to drill a well through the CO2 plume and core the reservoir that's been contacted by CO2. So with that, I'll wrap up. And I want to make one final comment, because this was asked a couple of times. I've presented this now. And I started with saying that, CO2 storage is a big problem. CCS needs to make a difference. This is an annual update that's published by the Global CCS Institute. So you can go look this up online. There's their website, globalinstitute.com. They published this in December. And what this graph shows is kind of an interesting commentary on political and public acceptance of these CO2 projects. If you look at 2010, what this graph shows is million tons of CO2 injected per year from 0 to 400. Then the color scales is the basically developmental status. So operational versus building it, planning, and early planning. So you can see in 2010, kind of globally, we were injecting around 5 to 10 million tons of CO2 per year. And we had plans to do, another sort of maybe triple that. And then for about 5 years, we were all fired up. And then for some reason, the media, NGOs, governments decided that this was not a good idea. And so, basically it went to sleep. And about 2018 were the first global studies that showed the difference between doing nothing. So the cost of doing nothing. So what started this uptick again that we're in today was a conversation about the fact that, yeah, it costs money to do this. Governments don't want to pay for money to do this. But if you don't do this, what are the costs of doing nothing? And so where we started to see interest in CCS globally come back was sort of 2019, 2020, with the idea that, well, we better start paying for this. Now it makes sense to do these things, because if we don't, we're gonna have worse outcomes by not doing anything. So right now, you can see in 2023, 2024, you know, the planning for 350 megatons per year is underway. And now that's not 3,500 to get us a wedge, but it's a lot more than sort of 5 to 10 that we've been doing. So hopefully, with things like 45Q tax credits in the US, some of our federal tax credits in Canada, and some of this kind of work being taken to China and India, we can sort of start to see more and more of this stuff happen globally. So with that, I'll stop and I'll be happy to answer any questions you have. Thank you very much.
Yeah, so the formations you're injecting into our quartz sandstones.
Yep.
Basically, so you don't expect any reaction, mineral
No,
formation with the CO2.
No.
Quartz.
no, there's not a lot in there to create solid forms. Yeah.
Yeah.
We have had some issues very initially drilling the well with iron and iron sulfate in particular. So we injected some surface water into the wellbore during testing after they were told not to do that, and cut the permeability of the well in half because they created some kind of weird, you know, essentially. So the reason that they did that was there's about 100 ppm of sulfur, call it, whether it's it's probably sulfate in the water in the subsurface. Surface groundwater they used has 2,500 sulfate. So they basically pumped a whole bunch of 2,500 sulfate down in our wellbore, and all the iron species down there said, "Woo, sulfate, let's go." And our permeability near the wellbore went low. Yeah, dropped.
Jason. The little salt stalactites you have in your pore space.
Yeah.
What's the depth of penetration of the side of the pores of those forming? And, or do you think that can be in any way related to how the continuing pressure, injection pressure?
Yeah, we don't think they penetrate very far into the wellbore, because they seem to break off and leave a hole when they break off. So does that mean they're not there? There is dry out. So when you inject CO2 into that saline of brine, you dry out the rock and you expect precipitation behind the CO2 front. But in the supercritical CO2 plume there, you don't expect that to be, you know, it's not plugging the pores off because you're getting movement of CO2 away from the pores. So yeah, those are strange. That's a strange occurrence. To see that in the wellbore. So
do you think that could be relate to, everybody sure the curve where the injection pressure kind of drops?
Yeah.
To breaking that initial kind of salty stalactites off?
No.
Near for.
No, that doesn't seem to have any effect. No, it doesn't. It seems to be more cooling yeah. Those stalactites, the interesting thing is they don't occur at all the perf intervals. They only seem to occur at the lower permeability intervals. So, you know, you can imagine there's 4 intervals we're injecting in, and we do spinner surveys to see while we're injecting which one's taking all the CO2. And we also do saturation logs. So you basically run a tool down the borehole and measure the saturation distribution out from the wellbore. And those will show you, you know, how far away from the wellbore the CO2 plume is over time. So going in and going out. And yeah, those are, yeah, we've had, so we had some people from Lawrence Livermore who, you know, sort of wrote Pitzer equations and Freak and all that stuff. They tried to model those salt in supercritical CO2, and they struggled to get it to work because the ionic strength, 330 gram per liter brine with all those weird minerals and calcium and stuff, it's a tricky thing to get it to model properly with CO2. Yeah.
Out of curiosity, has anyone looked at microbial activity?
Yeah, we get asked that all the time, and the answer is no.
Yeah.
And the reason why we didn't do that was because, it's virtually impossible to think about how would you collect a sample that you couldn't argue you introduced in the subsurface. So, you know, we've been asked about, will the CO2 destroy any microorganisms that are down there? And we said, well, you know, if you can figure out how to get a sample of those organisms to the surface without, I mean, it's a 3,400 meter steel pipe with, you know, pipe dope and all kinds of rubber and weird stuff. There's a nitrogen column on the top of it to keep it below the frost depth and all kinds of weird stuff. So you know, even to the point of when we did the MDT samples, could we collect a sample and you somehow have to sterilize the sample chambers and all the gas, like everything. So it's pretty hard to, I don't know. We don't know how to do that.
There's gonna be noise, but I wonder about EDA or something like that. Dave.
One of the criticisms, at least that I heard around here about carbon capture, was the energy required to do it. So I saw that the power plant output went down a little because presumably you're sucking power.
That's compression. Yeah, that's compression loss.
There was this, I don't know if it was a old wives' tale or what, but it basically said you were going to need a single power plant to do 2 standard power plants.
No.
Is it not that extreme?
No, well, you could see that we weren't sure exactly what it would be because you have to fire it up and get it all working, but the plant was designed to be 150. It was 139, so they designed it sort of 150, and the net ended up being about 120, depending on how they run it, about 125. So you're losing about 20 out of 150.
Okay.
So about 15–20%, maybe something like that, 15%. The other thing I'll say is that this was the very first sort of globally capture unit at a power plant. We used this is a CANSOLVE amine system that is proprietary to Shell. It was designed for hydrogen reformers at refineries. And so it was not designed for fly ash and coal. And so the first thing that happened when they turned this thing on was it works beautifully, but the amine gets polluted by ash and the coal. And that plugs all the screens in the whole system, which means they had to shut the plant down. And what they actually had to do was build a bypass loop with separate filtration systems so that when the filters start to plug the amine system, they actually divert to a freshly cleaned one and clean the old one. And they switched it. So SAS Power has got another power plant right near this that does another huge big, it's called the Shan power plant. They did a feasibility study on doing this at another power plant. They would not use this particular system. They'd use a Mitsubishi capture unit that's not only more efficient, so less parasitic load on the compressor, but it also is more efficient in terms of you won't have the ash problem. And so I think what's the one Petronova, what's the one in Houston that started up, almost got running and then got shut down? They used the Mitsubishi one. And SAS Power has published a feasibility study saying that they figure that the version 2, with what they learned on version 1, they could cut the cost by between 20 and 40%. So in other words, it would cost 20 to 40% of what they spent on this one to do the second one. So that's a pretty big savings.
One last question.
Yeah, no.
So is it capturing all the CO2? Okay.
Oh, yeah, 100%.
Okay.
Any other questions? I was gonna check with folks online.
Yeah, check online. And meanwhile, I'll do this
Chat.
question while you're doing that. What's your question? Go ahead.
Any questions online, folks? I'm not hearing anybody. Go ahead,
Questions? Do you have a question?
Jennifer.
Right, I can ask one. What's the injection temperature and pressure of CO2?
Smokes, that's a lot of people.
Good question. It depends on when. So bottom hole temperature is about, depending on which depth you're at, around 117 degrees Celsius. CO2 comes in about 40. So if you run the thing to steady state, you would cool the whole thing down to about somewhere in that, like, I think we had the lowest we get somewhere around 60 degrees, because as you let the CO2 go down, it starts to heat up as it's traveling down the borehole, and so it's somewhere, downhole temperature around 60 degrees, something like that, running for a long time. Bottom hole pressures, again, depending on, so ambient is around 30 MPa. Our kind of injection limit's like 39, and the well works somewhere around 34, 35, 36 MPa, somewhere in there, that range. Again, depending on how much CO2 is going in there for how long, how fast they're pumping in.
We're at 10 after. Thanks, Ben. I appreciate it. Thanks to everybody.
Thank you all. Thank you for your help.
Yeah, no problem. Sorry about the volume for a second.
That's a lot of partners. I wonder if you guys co-op or that.
Well, we got. Well, that's not me, that's KTRC does all those